Hello everyone, and thank you for coming. I'm AFrançois, a PhD student from University Paris-Cité, and I'm supervised by Joan Glonès and Pietro Gori. We'll talk to you today about weighted metamorphoses and the way and how I use them for registering image with different topologies. So, these two images are just here for having a glance of what the data I'm registering looks like, and we register healthy brain template of MRI image on images of patients who have a glioblastoma, which are a very malignant form of brain cancer. So just to give you a bit more details, so we are registering as a source image the MNI template, which is an average of 40 healthy patients, and it is a very good representation of what is a healthy brain. And we are trying to match it with images which have a glioblastoma, and we are, let's say, composed of two parts. A first part, which will be the necrosis, and which is the hurt of the cancer growing, and it will induce a topological difference in the image, and obviously it will, by growing, push the matter and the surrounding tissues and induce a mass effect. And there will be some infiltrative part, which is called the edema, and which will cause like an intensity changes into the brain. And obviously these data, they are MRI, so they are 3D data. And so here you can see this in the tool that I've developed through my thesis, and which will be available in my GitHub page. So, in order to do the registration, I'm using LDDMM and or Metamorphosis. For those who are not familiar with, I will just have a very quick, I just will say what is LDDMM. But this is a tool, let's say, in order to match two images by a deformation, which will be induced by a flow of vector field. And it has a very interesting property to link two images by a diffeomorphism. And this diffeomorphism can be used as a norm in this diffeomorphic space, which is Hilbertian. This is very interesting. And Metamorphosis is even more interesting as it combines LDDM and the diffeomorphic property with intensity changes, allowing to match images with different topology. And so, if we just look at the mathematical formulation, it is equivalent to solving this minimization problem, finding the ideal vector field, temporal vector field, and ZT, which will be a temporal image which can have negative values. And what is important here is that I1 is obtained by solving a variational problem, or variational equation, and we have here the temporal derivative of the image, which will be the application of the vector field plus some intensity changes. And so if we have mu here, which is a parameter set to 0, we have LDDMM. So to just give some very, very small details, so this is the cost we're minimizing if we are doing metamorphosis. So this is the regularization term. And so we solve this problem by geodesic shooting, and we integrate over the geodesics with this set of equations, which does look like very much as the Navier-Stokes equation for fluid dynamics, and that just is making pretty pictures, but that's interesting. So let's examine a first example. If we want to match this source image on the target image, and let's say these 4 shapes here are 4 organs, and it happens that the target image have cancer that grew inside, pushing the surrounding tissue here. If we try to match these 2 images with LDDMM, obviously it's not a well-suited method to use it, but we have very, very bad results. If we try to use Metamorphosis, which we have the intensity changes here into and we have the cancer. However, the organs here are explained by intensity changes and not by deformation, which is not the result we wanted. So we tried to we made a simple change to the Metamorphosis algorithm, and to try to add intensity changes only where we wanted. So to do so, we changed our cost, our regularization term, and here we put the mask, a mask M here, into the norm, and so we constrain Z only where M is non-zero, and this is not a binary mask, for example. And what is very nice is if we compute the Euler-Lagrange equation of the regularization term, we have this set of geodesic equation, and what is important here is that we add intensity changes only where M is non-zero, and this is exactly what we wanted. And so if we just try to match this with a constant mask, we see that we managed to register well the two organs here. However, if the organs were superposed on the target image, we see that they got stuck, and we do not achieve to register them properly. So to do so, we thought of making the mask grow. So we have not a constant mask, but a temporal mask. And to construct the growing mask, we set M1 at time 1 as the segmentation of the cancer, of the topological difference. Then we initialize M0 as a small ball at the center of the cancer. And then we register M0 to M1 using LDDMM. And then, therefore, we have a growing mask here. So now we see the results of WM with a constant mask and with a growing mask here. And we see that we managed to register quite well the 2 images. I validated my algorithm on 2D images from the BRATS 2021 dataset, and we validated with a die score of the deformed ventricles, the segmentation of the deformed ventricles with the ventricles of the target image. And then we did the die score, which is a measure to see how well the two things are superposed. And since the paper submission, we made the algorithm work in 3D. And so here you can see one visualization in my tool that I have built. And we see that we have a quite good registration here with the mask growing here, and you see the image evolving, the target image, and the comparison of the target with the images. So as a conclusion, I just want you to remember that this is a good algorithm for registering an object with a topological change that is growing, and I just want to emphasize that it works on individual images and do not require a big data set, as it is not a machine learning algorithms. And finally, I have to admit that it can be improved, but we are working on, and I hope that you will hear from us very soon. And obviously check up my GitHub channel where all the code is available to you. Thank you very much for your listening.